Hello again. Good afternoon. Uh, in this session, I'm going to tell you about visibility and sky-view factor computation and solar irradiation analysis using visibility computations. And at the end, I'm going to show you something about computing so-called solar envelope.
Can you put this? Sorry.
Yeah. Do you have my full screen online? So, again, there's an old version of this lecture online. So if you want to make it different from the old one, then ask good questions, okay? And I'm going to explain something about visibility on a little paint canvas here on my laptop. So it will be recorded also in the video. Okay, so first of all, what is special about solar analysis, and why did I choose this example? Because for obvious reasons, namely that the society is going through an energy transition, and solar energy is very important. But solar energy is also indirectly related to heat and overheating problems in cities and health because of daylight, vitamin D, depression, you name it. So solar energy is the source of most of forms of energy on Earth also, except for nuclear energy, right? So all other kinds of energy are one way or another coming from solar energy. So it's very, very important. And interestingly enough, from a geometric computing perspective, what most of these solar analyses have in common is the concept of visibility, right? Which is a geometric concept that is based on the notion of intersections between point sets or intersections between geometric objects, mostly the intersections between rays and triangles. So this is like the bread and butter of solar simulations, the intersection between rays and triangles. So by now you are pretty much equipped to understand what this intersection is all about. It's about finding a point in common between two loci or two locus representations of spaces. One of them should be the ray as a locus of points in the direction of a direction vector and in the positive direction of parameters multiplied by that vector, plus an origin point. And the other one is a simplex representation of a triangle. Why a triangle? For the obvious reason that most surfaces that we are interested in can be represented as triangular meshes, right? And there's nothing ambiguous about a triangle. It's a simplex space, it's a convex space, it's flat, and there's no ambiguity in terms of how it reflects or receives a flux of light. This notion of flux is very important. If you want to understand it conceptually, you can think about catching fish in a river in a direction perpendicular to the stream of the river with a net. So if you're perpendicular to the direction of the stream, you're very efficient for catching fish, salmon, let's say, right? But if you hold the fish net in such a direction that the normal vector of the fish net is perpendicular to the stream, then you're not effective at all, right? So the normal vector of the fish net should be parallel to the stream direction, right? If you want to catch anything. That is the notion that is known as flux in physics. So it is always about the dot product. Yeah. So deep down, the concept of visibility is also about the dot product. But the dot product is just about two vectors, and two vectors, neither of them has any location. So it just shows the possibility of having an intersection. It doesn't show the actuality of the intersection. The actuality of the intersection has to be computed in terms of the finding a point in common between two loci or two locus representations. So it turns out that actually, if you write down the equations, we have explained one very simplified or let's say elegant or summarized vectorized algebraic way of computing these kind of intersections in our recent paper about voxels. But to summarize the whole story, it's about computing the intersections between loci representations as such equations of planes and rays being intersected to each other means solving a system of linear equations, right? And the answer to the system of linear equations is the solution to the system of linear equations is the intersection point. The tuple xyz that can satisfy the two equations at the same time. Yeah. So if you want to understand how it works, then you need to think about this one. The ray as a locus. Yeah.
That's great.
Was it showing something
No.
so far, or
Yes.
it was all black one? Just what happened? It just went off.
Yeah.
Show my screen sharing in the classroom.
Anyone know how this works? Can try to turn it on like that. To this.
Should have this. Do you have USB?
Yeah, USB-C.
Do you have another USB?
On the other side, no.
Okay.
don't know. It's working now? Ah. Yeah, it's
Yeah.
back.
Okay.
Okay. Okay, so maybe I can cut it short and just show you.
The algebraic representation of the intersection that I was talking about. So first of all, we have a ray and a triangle. So how do we represent a ray? That's the first question. So the answer is that we represent a point on a ray as the locus of points whose coordinates can be computed at one point on the ray plus some parameter r times the vector d. I think that should be pretty clear why this works. Because of the vector addition principle, any vector like r times d, sum together or added to the other vector, the position vector p, gives us a new point, p prime, which will be definitely on the ray. And if r is a positive number, then positive real number, we virtually have all the infinitely many points on the ray, right? And similarly, we can represent a triangle with these conditions, with the conditions that I told you. It's a span between two vectors u and v, and parameters s and t multiplied by u and v and added together, added to a center point c, right? And I told you that the additional requirement that s and t should sum up also to 1, right? So finding an intersection actually means finding a p prime that can satisfy both of these equations at the same time, basically equating these two equations together. If you put these two equations together, you arrive at this one. P minus C equals minus R times D plus SU plus TV, right? And if you arrange this algebraically, you will realize that you have three vectors, 3 by 1, negative D, U, and V, which can be put together into a matrix, 3 by 3, and three real parameters, R, S, and T, that can be put together as a vector, and another vector on the other side, P minus C, 3 by 1 also. So therefore, we have a system of equations, a very elegant system of equations in the form of AX equals B, which is pretty straightforward to solve using this determinant and the matrix inverse for the case of 3D. So we compute the A inverse. If A is this matrix, 3 by 3, we compute the A inverse. which is 1 over the determinant of the matrix multiplied by this adjugate matrix. I think it's called an adjugate matrix. Anyway, this is about computing an inverse of a matrix. And when you do the math, you will end up with these equations for R, S, and T. So actually solving the first one is already enough, because if there's an R, we just need to check S and T if S and T meet the conditions. If there's an R, that means there's at least 1 point on the ray that satisfies this equation, but S and T should also be smaller than 1 and add up to 1. Then we have found our intersection point with the triangle. And think about the determinant. The determinant determines whether this system of equations actually has a solution or not. And the determinant will be 0 if the ray happens to be parallel to the triangle. In that case, it is impossible to have any intersection whatsoever, right? Therefore, the system of equations cannot possibly have a solution. Therefore, the determinant is 0, and 1 divided by 0 is undefined. So in an algorithm, you should check that and avoid that by making sure that this dot product in the denominator is not 0. And that's what we're doing. This is the paper that I referred to in the documentation of the code. Okay. So back to so this was the story that I wanted to show on a blackboard, but I figured this is written more clearly in the paper. So I showed it over there. Anyhow, and similarly, you can do such computations on a 2-dimensional surface with lines and rays, and you can compute visibility polygons, which are star-shaped polygons or star-convex polygons. I told you already the meaning of star convexity with pentagonal stars and hexagonal stars and so on. These are generalizations of those objects, visibility polygons, which have a kernel. So, but they more or less look like baked eggs that have, you can think of the egg yolk in the middle from where everything is visible, right? So these are visibility polygons. And visibility polyhedrons can be also formed in 3D space in the same way. And there's one particular visibility polygon that is the one that we are using in the workshop in the afternoon for computing the so-called sky view factor. The sky view factor is an index or an indicator that basically measures the degree to which the full sky is visible from a certain point, usually in an urban space. But it can also be applied to all kinds of spaces, open spaces in nature. You can imagine that this index should be less than 1 for areas like in valleys between mountains, because if you're in a valley, you don't see much of the sky. And also in the so-called urban canyons or urban valleys, you don't see much of the sky. Why is that even important? Because that's how most buildings cool down during the night, by radiating their heat towards the sky. If they cannot see much of the sky, they cannot easily cool down, they heat up. That is one of the main reasons we have the so-called urban heat island effect in cities, right? So, as you can imagine, this is a concept very much related to visibility, which exists everywhere in natural landscapes and in urban landscapes. So it is a very useful thing to compute the sky view factors, because this factor can actually indicate the possibility of having this urban heat island effect. So let us focus on how this can be computed. We want to get into a number ideally ranging between 0 and 1 that can indicate such differences. So it should be larger for an area like this valley, and it should be smaller for this area because this sees less of the sky, but in 3D space. it is about computing integrals, surface integrals. I see everybody smiling. Surface integrals. Again, you remember something about surface integrals from high school? Yes? Long time ago. So here, in the old version of this, I've explained the whole idea of integrals very much in detail, but now maybe I can shorten it a little bit. Integrals and differentials are the basis of the calculus, and if you want to get a very good understanding of integrals, then you should have first a good understanding of differentials. Differentials are about these differential elements, in fact. Finding the derivative of a function or the differential of a function is about finding the rate of change in that function. The rate of change of the dependent variable with respect to the rate of change of the independent variable. How much does the price of oil change when we go forward in time? How does the height change when we take a step forward on this landscape? And so on and so forth. This ratio, this quotient, is called the derivative of a function, assuming that one variable is dependent on the other. And there is a particular such differential, which is the area under a curve, under the function representing a curve. That's a particular one. This area has a property that if you compute its derivative, the derivative of that area under the curve of that function actually equals to the function equation itself. That is the fundamental theorem of calculus, right? And this property can be used to find the so-called antiderivative of a function and use that to compute surface integrals and curve integrals and so on. So in other words, when we want to compute the area under a function, we have to figure out what function could have a derivative in the form of this f of x. And if we figure out that function, then we can use that function to compute the area. Yeah. So I think this is pretty much the shortest possible lecture about derivatives and integrals, right? So let us begin here. Let us see it in action here. So ideally, we are representing a hemispherical surface in this form. We know that it's not continuous. It's going to be a discrete such surface, but for the sake of the argument and for the sake of computing this as a closed form formula, we start with the notion that this is going to be a continuous surface. But effectively, we are actually making it as a little mesh, yeah, with vertices and faces. But for now, let us think of it as a continuous surface. So we need to think about the so-called area element, which is a two-dimensional differential element. Why two-dimensional? Because obviously this is a surface and it's two-dimensional, and so it should be consisted of two-dimensional surface elements. And you need to understand a little bit the notion of spherical coordinates. So I already showed you something about nerve surfaces and the fact that you can have a correspondence between two-dimensional domains on in the space of R squared and two-dimensional domains on surfaces. This is the best example of such correspondence between two-dimensional ranges of numbers and surfaces that represent a mapped version of those numbers, namely the surface of the sphere, which should be ideally the most familiar surface to you all because you're geospatial experts, right? So with latitude and longitude, you are referring to basically coordinates, rectangular coordinates in a rectangular domain. That is why it is so common and convenient to represent maps of the surface of the Earth as a rectangle. With 2 parameters, you are actually referring to a 3-dimensional point. Isn't that the case? Yeah. So how is that possible? You have to figure out a mapping or an embedding of these 2 coordinates. Let's call them theta and phi. Theta for the azimuth angle or the longitude angle, and phi in the physical convention for the elevation angle or the latitude angle, if this is half of the globe, right? And so if we have just theta and phi, we can uniquely represent every single point on the surface on the condition that theta ranges between 0 and 2 times pi, and phi ranges between negative half of pi and positive half of pi, something like that, right? But here we have the hemisphere, so let's say phi ranges from 0 to half of pi for the North Pole, right? Or Z in this case. Yeah. So a single point here can be uniquely represented with theta and phi. How is that possible? So if you can read this, r times cosine of phi actually computes the shadow of this point or this vector, let us say, this position vector to the point, has a shadow on the zenith axis or the z axis, which exactly has this length r times cosine of phi. If we compute phi from the plane, xy plane, yeah? Sorry, from the zenith, yeah? If we start calculating phi 0 equal to the zenith direction, then our cosine of phi will be the shadow of this vector on the zenith direction or the z-axis, yeah? And our sine of phi will be the shadow, the length of the shadow of this position vector on the plane, xy plane, right? So our sine of phi times cosine of theta will be the shadow on the x-axis or the x-coordinate of the point. And our sine of phi times sine of theta will be the shadow on the y-axis or the y-coordinate of this spherical point. So actually, with only 2 parameters, phi and theta, we can represent all the points, all the 3-dimensional points on the hemispherical surface. That is exactly how we're going to compute a bunch of points with which we're forming rays to shoot towards the sky in the afternoon. Yeah, practically. So now you understand all of these things, but what is the area element? The area element is can be understood as the little rectangle that can be formed by multiplying these 2 little lines. So first, let us think about one of these little lines. Let's think of an infinitesimal change in the direction of theta around this point. If theta changes a little bit, so a differential of theta multiplied by this length of this radial point, arc cosine of phi, gives us the arc length. Basic trigonometry. The arc length equals r times theta. This is a differential of theta. So this little angle span has the length differential of theta multiplied by this arc, by this radius, gives us the arc length. Similarly, the other arc length becomes r times differential of phi. So you have 2 arc lengths for the 2 sides of this little rectangle. Multiplying those 2 gives you the area element. So r cosine of phi times differential of theta times r times differential of phi, right? And therefore, if we want to compute the surface of this hemisphere, we have to integrate this area differential over the ranges of theta and phi. And long story short, we figure out which functions can have which function can have a differential in this form, and then we compute that function, and we take out the first one, which is for the range of, I believe, phi, and we are left with the range of theta, and we discretize one of them, which is for the range of theta. We discretize the range of theta because for the range of phi, it is kind of straightforward to shoot rays in these directions. Let's think of one track of these rays that we are shooting towards the sky. We are going to figure out the first phi angle below which nothing is visible from the sky. So the first intersection can be recorded, and we can figure out what is the phi angle. Yeah. So in that direction, we can still somehow think of the space as a continuous space. So we don't need to discretize that direction. The direction of theta, however, has to be discrete because we can only afford to have a discrete number of such tracks of ray casting. So the direction of theta is discretized with a sum, and therefore we get into this formula. Long story short, 2 times pi times 1 minus sum of sines of these gamma angles. Gamma angles are the angles, the first angles at which we hit something from the sky if we start computing from the zenith. And then we keep track of these angles, and then we get a picture of what is visible from the total surface using this formula. And this formula actually ends up being between 0 and 1. Yeah? And this is our sky view factor. This is literally exactly what we are going to do in the afternoon. We're going to use a library, a geometric library, Open3D, to compute these intersections, record the gamma angles, compute this part, the difficult part, which is probably the most difficult part for you to understand right now, is the surface integral. This actually ends up being one single line of NumPy code. The more difficult part in code is actually getting these gamma angles out of the intersections and putting everything in the right shape, array shape, and so on. Okay, so here I'm giving some tips for computing this using the Rhino Common library for mesh ray intersection methods. You can also see a little exercise for yourself in the notebooks of the notebook of the afternoon workshop for completing this exercise with the TriMesh library if you want to really understand the algorithm. But it's going to be slower than the algorithm that we have already implemented, because the one that we've implemented is implemented using Open3D, which is much faster because it can take a whole bunch of rays and intersect them in one go with its C++ implementation with a whole bunch of meshes and give you the answer. But deep down, all of these algorithms do the same thing, which is finding a point in common between loci of a ray and a triangle. But the mesh consists of many, many triangles. So these kind of computational processes are rather heavy. Okay, so let me tell you a little bit also about solar irradiation analysis, because obviously one of the main uses of 3D models, this course is about 3D geospatial modeling, is solar simulations, because a lot can change between different situations in cities because of the visibility or the invisibility or the relative visibility of the sunlight, because of all kinds of possible obstructions in urban environment, from other buildings, from trees, etc. So again, the whole idea is about visibility. this is a refresher about some things that you supposedly all know already about the so-called solar geometry. Why do we have seasons? Refresher from primary school. Because of the distances to the sun changing or not? No, it's because of orientation. It's because of dot products. So the Earth spins around itself around an axis, revolves around this axis, which is declined from being normal to the plane on which it rotates around the sun. Right? First of all, let us be very clear about one thing. The sun is so huge and so far away from the Earth that in most practical applications, even in geospatial coordinates, the sun rays that we receive can be considered to be completely parallel to each other. So we're not talking about a point seeing the Earth. We are a point compared to the sun, right? So if you want to conceptualize the sun rays coming towards the Earth, you need to conceptualize them as a plane, not as a point emitting rays. Yeah, the sun is far from being a single point. It's a huge plane compared to the Earth. So imagine this huge planar object emitting rays to the surface of the Earth, and in half of the, let's say in the winter half of the circle around the sun, we receive this in the northern hemisphere. We receive these rays rather inclined, so their dot product or the flux with the surface of the Earth is less, and therefore we have the bend. And oppositely in the southern hemisphere. Yeah. So the more perpendicular the rays, the more energy they impart on the surface to which they're incident, right? So this is about the dot product, long story short, right? Or the flux. And actually in the following slides, I'm going to show you the kind of simplest solar model that you can immediately make as a little geometric exercise for yourself. But I also show you the more sophisticated version, which is about getting to the gory details of how exactly the sun rays are observed from the surface of the Earth and the equations of time and so on and so forth. But the baseline is this story of seeing some kind of a band of a spherical surface around the Earth from which you can conceptualize points. I told you that this is actually about the visibility of rays that are effectively emitted from a plane. But if you want to model sun rays, then it's very effective to model sun vectors. Because for every moment during a day, you only need a single vector to model sun rays. Why a single vector? Because that single vector can represent the whole plane, right? Because wherever you are in the vicinity of that area, unless you have a significant change in the latitude, you effectively receive the same sun rays at that moment in time, right? So because of this inclination angle, you actually get 4 special points through the circle around the sun. 2 points are called the equinox points, which are the points that the lengths of days and nights are the same, and you transit from winter to summer and vice versa. And 2 points which are especially important for solar analysis, which are the winter solstice and the summer solstice, around December 21 in the Georgian calendar, which is the most common one in the world. You have the kind of the lowest altitude or elevation angle for the sunlight in the northern hemisphere. So it's the kind of lowest point of the sun in your skyline in the northern hemisphere, and the highest point for the southern hemisphere, right? And the difference between the highest point and the lowest point, can you guess what how much it is in terms of angles if the declination angle is 23 degrees? The Earth's declination angle is about 23 degrees, give or take, right? So the highest point from which the sun is visible around here for a certain location, geographical location, is going to be, what is going to be the span of these points? If these points kind of represent all the possible solar vector directions. This is the simplest model that I was telling you about. Can you guess if you're on the equator, at the point of spring equinox or autumn equinox, the sun will be exactly above your head at 12 hours at noon, right? Right? And in this winter solstice, it's going to be negative 23 degrees below that point in terms of elevation angles from the zenith. And the summer solstice is going to be positive 23 degrees on the other side. This is the simplest solar model that you can think of. And putting these facts together, you can also observe that this base plane from which I'm making this model is inclined exactly how much? No. The base plane, the red one. So you go from the equator, you go to the north, and this surface starts getting inclined. If you go to polar areas around Sweden or Finland, this gets pretty much almost perpendicular to the surface of the Earth, right? So the only variable here is the latitude. Maybe also the altitude of the point in terms of how high it is above the surface of the Earth. But if we are computing this on the surface of at the sea level, it's only the latitude that changes, right? So with one angle, the latitude, you can orient the surface. So if I ask you what will be the most efficient orientation for a solar panel at a location, you should give an immediate answer to that. A plane that is exactly oriented towards the south and inclined how much? Exactly equal to the latitude of that point. This one. Because on average, this is going to be the plane on which you have the maximum flux over the year. If this is the only angle that you can have, this is your best bet, right?
Latitude.
Sorry?
Latitude of.
Latitude of that place, yeah, the latitude. I think this is pretty obvious from this picture, especially right at the bottom right. Because give or take, this is what we call the solar window, all the hours which actually matter in terms of sunlight. It is pretty impossible to have a direct sunlight around, I don't know, 6 o'clock in the morning in most cities because your sight line is most definitely obstructed, right? But plus minus 3 hours from noon, plus minus 4 hours from noon, those are the so-called solar hours, right? So this is the extent of this model, this little spherical surface. It's plus minus some hours from noon and plus minus 23.5 degrees from the latitude angle. We have a mesh, we have a regular grid of points on this spherical surface using P and theta angles. Yeah, and that's the simplest solar model that you can make for yourself. Yeah. And this is the most sophisticated version, which includes the equation of time and slight differences in uh, uh, in the location of the sun. And these curves are there if you actually use the actual equations for computing solar angles, and you plot the points during the same hour throughout all these months, you will get this so-called I've forgotten the name of these points. They have a fancy name. These curves. The points are actually not real points. We just use these points to indicate the orientation of the vectors that represent the normal of the plane that can represent the sun. This is a long story, but at the end we show them as little points. And conceptually, yes, if you badly want to conceptualize them as little points, you can draw little arrows from them and think of them as little suns. Yeah, but each of them is actually a plane or a huge disk, let's say. Okay, so these slides are about getting more precise with the hour angles and finding these fancy curves or the exact equations of time, which is used for finding these analemma curves. Yeah, I think they're called analemma curves. These particular curves, if you plot some positions in the sky at the same hour throughout the year, you will get a curve like this. That's because of the ways we compute hours. This is the story of the plane representing the sun and the angle at which it is incident to the surfaces on Earth, and the story of seasons and all that. And the declination angle of the sun angles being computed in terms of zenith angles, and the notations for the formulas that are used here. These are the exact equations. I don't bother with these equations because you can get them from libraries. That's not the most important thing. The most important thing is to have a very clear conceptual idea about this simple model. And if you need the exact angles or the exact position, exact orientations of the solar vectors, you can get them from some libraries that compute this exact angle. And what happens if you put, let's say, 2 and 2 together? The amount of the sky that is visible, the sky view factor, and the solar directions. Then you can pretty much estimate the potential of a location for receiving sunlight throughout the year. Right? The part that is not visible is not visible, it's just not visible. Okay, so no matter what you do, this is the part that the part of sunlight that can only be received as diffuse sunlight because of all the diffusion of light through the atmosphere of the Earth. But you don't have direct sunlight, so I wouldn't count on it for energy or for warmth. But still, you can get also some amount of diffuse light, which is pretty much proportionate to the sky view factor again, because it has to do with how much of the sky you see, the diffuse light, right? Why do we have a blue sky? Because of the atmosphere. If there was no atmosphere on Earth, we would see a black sky and only see a bright point for the sun, right? So the diffuse light also has something to do with the amount of visible sky. So therefore, you see the importance of the sky view factor. And if we put all of these things together and think about something like a form-based code for regulating the so-called right to daylight or the right to sunlight, and we want to ensure that all buildings in a neighborhood, even after building a new one, will have the same right as they used to have before this new building was to be built. Then we can think about the proposed volume for this new building to be added as a bunch of voxels. And think about the voxels in terms of how once they are obstructing the visibility of the sun for the neighbors, for the windows of the neighbors, for the facades of the neighbors. And if we start shooting rays from the facade or the windows of the neighboring buildings towards this building, you soon realize that some of the voxels in the proposed volume for the building are almost always in the way of the neighbors getting sufficient sunlight, and therefore they're bothering the neighbors. So maybe they can be removed to ensure that the neighbors have sufficient direct sunlight with some standard. So you can play with these parameters and you can get a shape in which you can build something without bothering the neighbors. That's basically the whole idea of the so-called solar envelopes, which are perhaps the most famous kinds of form-based codes for regulating or planning cities in 3 dimensions or ensuring certain qualities. In some cities, like New York, I think there may be simpler form-based codes to ensure that buildings taller than a certain height should have certain angles towards the sky to somehow ensure that the urban canyons at the bottom or at the street level are somewhat acceptable in terms of visibility. Different countries have different versions of these kind of codes for the obvious differences in their climates and so on. In the northern hemisphere, in high latitudes, obviously daylight is a big issue, and closer to the equator, the overheating is a bigger issue. So you can play with these parameters and think about a whole range of such environmental envelopes that you can develop. Yeah? Okay, so the last one is an algorithm as a pseudocode for computing these solar envelopes, but this is something that we won't cover in the workshop for your information. And that's it. Questions? Everything clear? Yes? Okay. Any questions from the online participant? No? Okay, so I will see you in the afternoon for the workshop, and we will exactly do this computation of sky view factor in NumPy using Python and NumPy. Okay, see you soon.
Okay.